WPR number 4. With an absolute value inequality, we'd like to separate this into two inequalities, but you can only do that after you've cleared out all the other terms on the same side as the absolute value symbol. In this example, there's a 4 with the absolute value. We need to clear that out. So I'm going to go ahead and subtract 4 from both sides. Notice that I'm not taking the absolute value. I'm not removing the absolute value symbol as I do this. It's only now, after I've cleared out the other terms, that I can remove the absolute value symbol to create the inequality 3n minus 6 is greater than 18, along with the other inequality 3n minus 6 is less than negative 18. Switch and negate for the second inequality. So I will add 6 to both sides. 3n is greater than 24. n is greater than 8. Also, 3n is greater than negative 12. 3n is less than negative 12. So n is less than negative 4. Now we need to ask ourselves, is there a number that can satisfy both of these conditions? Is there a number that's greater than 8 and less than negative 4? Of course, the answer is no, which means this problem is an OR. Writing this on a number line, I would have the negative 4 on the left, the 8 on the right. There is no equal to symbol in these inequalities, so these circles are open, and we have ORs shading away from the center. When squaring a term, you are multiplying it by itself. When squaring a binomial, it's no different. This is a binomial. It has two terms. The first term is 3. The second term is negative 7i. When we square a binomial, we are multiplying it by itself, which means we are double distributing or foiling. So we'll get 9 minus 21i for the outer minus 21i for the inner plus 49i squared for the last. Now these two middle terms are like terms. They can be combined into minus 42i. We also have this final term, which is 49 times I squared. Now I squared is negative 1, so that means when I multiply the 49 times negative 1, it'll be negative 49. And now, again, I see that I have some constants. They are like terms. 9 minus 49 is negative 40. I'm left with negative 40 minus 42i. That is the final answer to this problem because these terms are not like terms. This does not have an I. This one does. When factoring a higher degree polynomial, look to factor out a GCF. In example 3, we can look to the coefficients and the variables for our GCF. 12 and 75 have a greatest common factor of just 3, t to the 8th and t to the 4th, because they are variables. We'll have a GCF of the t to the lower of the two powers. To finish factoring out the GCF, imagine dividing this term by the GCF. Do it one step at a time. 12 divided by 3 is 4. T to the 8th divided by t to the 4th is t to the 4th, resulting in a 4t to the 4th inside. There's a minus in the problem. We will bring that down. And now we are going to, again, divide 75t to the 4th by this GCF. 75 divided by 3 is 25. T to the 4th divided by t to the 4th is a 1, and 25 times 1 is just 25, so we won't write the 1 down. Often, when factoring a higher degree polynomial, you will need to factor again. This is called factoring completely. This is the case in this problem. We have a difference of two squares here. The square root of 4t to the 4th is 2t squared. And the square root of 25 is 5. We will alternate the signs, and we will look to factor again. Now, this is definitely not, this is definitely not a difference of two squares. It has a sum, and neither of these terms are perfect squares. This does have two terms and a difference. It's a difference of two terms, but not two squares, because again, neither of these are perfect squares, which means that in this problem, I'm done. with fractional equations, we are looking to eliminate the denominators altogether. That's different than what we do with a complex fraction or when we're adding or subtracting fractions, in which case we're trying to get the same denominator. Here we're trying to get rid of these denominators. We can multiply both sides by the least common multiple of 4 and a plus 3. That would be 4 and a plus 3. So I'm going to multiply that by the term on the left. And by doing so, I'll get rid of this 4 in the denominator. And on the right, I will multiply also a 4 and an a plus 3 by the 8 over the a plus 3, which results in the a plus 3's canceling out. So what I can do now is I can reduce and write what remains. Well, the a plus 3 times the a minus 1 requires a little bit of work here. That's going to be a double distribution, so instead of doing that in my head, I'll just write it down for now. 4 times 8, I can do that in my head. I hope you can too. Now I'll double distribute to get a squared minus a plus 3a minus 3 equals 32, which I can simplify to a squared plus 2a. Now I have this minus 3 here. I'm going to bring the 32 over as a minus 32. The result will be a negative 35. And of course I could factor this using a method known as completing the square or factoring. But it looks like this will factor into a plus 7, a minus 5, and the a plus 7 equals 0 gives the root a equals negative 7, and the a minus 5 gives a equals 5. I should check to see if either of these would give me a denominator of 0 here. Negative 7 plus 3 is not 0, and 5 plus 3 is not 0, so it looks like our answers are negative 7 and 5.